In this video, we will create a very nice and beautiful game concept that is great for using pixel art graphics. And as you can see, this is an unusual 2D game. A distinctive feature of our game will be the ability to rotate and inspect each item from all viewing angles, as if we are in a 3D game world. And to create such a wonderful pseudo 3D effect, we will use a technique called Sprite Stacking. And we will create such a graphics engine using the Python language and just one Pygame library. That is, it is assumed here that you already have some knowledge of Python and the Pygame library itself. And let's first understand what the Sprite Stacking technique is, and what underlies such a nice 3D effect. So the Sprite Stacking technique is quite simple. Imagine that you are looking at an object from above. Let's say I want to draw a chair, and then we start drawing each layer pixel by pixel starting from the bottom. That is, each layer will be a separate sprite, and in order to create a three-dimensional effect, we need to displaying the next layer, move it by some amount along the y-axis, and thus all layers form a whole object that is perceived by us as three-dimensional, although we use only 2D graphics. If you have difficulties with drawing such layers, then you can, for example, use the MagicaVoxel editor. There is such an opportunity as to automatically convert the drawn 3D object into separate layers, and for this, simply select the way to export the model as a slice. And as a result, we have an image in the form of a sprite sheet, in which the entire 3D model is divided into layers, and the numbering of layers starts from the bottom. So let's take this format for all sprite sheets as a basis in our project, and I propose to start by learning how to display such a sprite sheet as a pseudo 3D model using the Pygame library and the Sprite Stacking technique. So, the initial setup from which we will start working is the main file and the settings. In the settings file, we have a short name for the 2D vector, and the screen resolution variable, its center and background color are also defined here. The main file contains the application class, in the constructor of which we create the rendering screen, an instance of the clock class, and attributes for tracking time and delta time. Let's consider the methods of this class. In the update method, the frame rate value is displayed in the window caption, and through the clock instance we get the value of delta time. In the draw method, we paint the screen with the background color and do a frame change. In the check events method, a check is made for closing the window and for pressing the escape key, and when such conditions occur, we gracefully exit the application. There is also a method for getting the time that has passed since the application was launched, and its values are defined in seconds. And finally, the run method, which contains the main loop, and we call all the considered methods at each iteration. And to start the application, its instance is created, in which the run method is called. If we run the program, we will see a window of the specified resolution, filled with the selected background color, and the current frame rate is displayed in the window caption. Okay, and to go further, let's create a file called stacked sprite. In this file, we will create a class of the same name that inherits from the Pygame sprite class, which will greatly simplify our further work. The input parameters of this class will be the application instance, name, and initial position. Then we take these parameters into attributes, call the super method, and let's select for the test some rectangular surface painted in orange, and indicate the position of its rectangle in the center of the screen. So, in order to work with a class inherited from the Pygame sprite class, we need to create a sprite group, and accordingly call the update and draw method, specifying the drawing surface. Once we have a sprite group, we can import our class and create a test instance of it. And in order for our instance to be automatically added to the sprite group, we need to access this group in the class constructor and pass it to the init method of the super function. This way we can see our test sprite, and this was another preparatory step so that you understand how to use the Pygame sprite class and sprite groups, since most of the work will be based on this approach. And note that the self-image attribute is set to the image we want to draw on the screen, and it must be in the form of a Pygame surface. So at the next stage, we have to do the following. We need to form a surface of such a size that we can place all the layers from the sprite sheet on it, taking into account the offset along the y-axis, and also implement the rotation of our object so that it is perceived as three-dimensional. But before that, we need to select all the layers from the sprite sheet so that we can work with them as separate images, so let's do this work first. So I put the van sprite sheet exported from MagicaVoxel as slices into the stacked sprites folder, which is a subfolder of assets. And here it is important for us to know the exact number of layers for each sprite sheet. Then in the settings file we will create such a data structure as a dictionary of dictionaries, which will be very convenient in further work, and call its attribute stacked sprite, and here we will describe our sprite sheet. Let's specify the path to it, the number of layers and some scaling factor to set the final size of the object. And then in the stacked sprite class, we can access all the attributes of the sprite sheet using the value of the name input parameter. And now I propose to write a separate method for extracting each layer from our sprite sheet as a separate Pygame surface. So let's call this method getLayerArray. Here we first load our sprite sheet, and then we scale it, and as you can see, we conveniently get access to the attributes of the sprite sheet. We also need to calculate the height of each layer. Obviously, if we divide the total height by the number of layers, we get what we need, and since I allow floating point scaling factors, it's better to recalculate the total height of the sprite sheet to avoid errors. And then we go head on, extract each layer using the subsurface method and put it in the layer array list, and at the end we reverse it since the layers start from the bottom. Now let's use this method to get an array of layers in the class constructor, and by the way we can display these layers. Let's say in the update method for self-image we can assign a layer, the index of which we will calculate from the current time value. Also do not forget to get the rect values from the current layer and indicate its location. And do not forget, when creating an instance of our class, we need to change the name to van, and for clarity, we will increase the scale. If we run the program, we will see a display of all the layers that we have extracted from the sprite sheet, and now we need a method that will shift these layers and we will get the desired result. And for this we will write the getImage method. Here we will do this, we will get the size of the image from the lowest layer, and then we will form a transparent surface of such a size that its height is increased by the number of layers, taking into account the scale. And then we blit all the layers onto this surface, shifting them up along the y-axis, while also taking into account the scale. And as a result, we have a formed sprite that we assign to the self-image variable, and also get the values of the rect from it, while setting the rect position taking into account the self-pos initial position variable, and making an offset to the center, since it is more convenient for the center of the coordinate system to be the center of the screen. And let's then call our method in the update method. Well, for now it is difficult to evaluate the result, so I propose to implement rotation for our object. Let's define an angle attribute that we'll get using the getAngle method, and we'll also calculate the angle based on the time value. Then we call this method before the getImage method, and now after getting the size of the bottom layer, we rotate this layer by the angle value, and we also need to rotate the next layer before blitting it onto the surface of the sprite. Thus, we got our object, but as we can see, it is not displayed quite correctly, since the fact that the y-axis in the Pygame coordinate system is directed downwards is not taken into account. And then let's apply the flip method to the generated sprite surface and run the program again. And as a result, we get a display of a sprite object, which is perceived really as three-dimensional, and as you can see, using the sprite stacking technique, you can get a rather interesting and original pseudo 3D effect. Well, now I propose to add one more object to our scene. So in the staked sprites folder, I have another sprite sheet, and it's not hard to guess that this will be a tank. Let's then define the attributes for the next object, that is, specify the path, the number of layers and the scale. After that, we return to the main file, and we can add a second instance of the stacked sprite class with the tank name parameter, and at the same time specify the location of objects on the screen using the pos parameter. Let's run the program, and there are already two pseudo 3D objects on our screen. Everything looks great, except for the performance of the program. At the moment we have a very low frame rate, and further development of the game with this approach is out of the question. The reason for this is a very resource-intensive rotation operation, and since Pygame is a wrapper over the SDL library, this rotation operation is performed on the CPU side. But there is a way out. In the case when many rotation and scaling operations are used, we can make a caching system, that is, we will pre-render the rotations of these images in advance, and we will use them as simple images without loading the CPU. So let's imagine one rotation of 360 degrees, and let's say we divided it into 8 equal sectors. That is, we chose the number of angles equal to 8, these angles are the same and we call their value the viewing angle, and it is obvious that the viewing angle is easy to calculate knowing the number of angles. In other words, for each sector we will pre-render a sprite that is visible at a certain angle. Here is an example where there are only 8 sprites, but the larger this number is, the smoother the rotation of the object will look, but it does not need to be rendered for all 360 angles, and achieve a smooth rotation is possible for much smaller amounts of angles. Let's go back to the settings file and define the number of angles. Here it is important to note that this number must be a multiple of 360. And then let's create a file called cache. In this file, we will write a class of the same name. In the constructor we will define a dictionary for the cache of stacked sprites. Based on the value of the number of angles, we will calculate the viewing angle, and we will call the method to get the cache of stacked sprites. In this method, using a dictionary for attributes, we will get the names of the objects. This is now Van and Tank. This name will be the key in the cache dictionary, and the dictionary will be its value, and similarly, with the key name rotated sprites we create another dictionary. Such a structure will come in handy in the future, since we will do the pre-render not only for rotating sprites. Then, using the name of the object, we will access the attributes, and we also need to get an array of the layers of the current object. To do this, we are from the stacked sprite class, just cut the method to get an array of layers and paste it into the cache class. But here I propose to get rid of the self parameter, and just pass the attributes to this method. And the last step is to call the run pre-render method, to the input of which we will pass the name of the object, an array of layers and attributes. And in this method, we will iterate over the number of angles, and here again we will cut out the code from the getImage method of the stacked sprite class. Similarly, we remove the self parameter here, and we need to multiply the angle index by the view angle value to get the required angle for rotating the layers. And it remains for us to place the resulting sprite image into the rotated sprites dictionary for each angle index, and our cache is ready. Then let's import the cache class in the main file, and create an instance of it. And now we need to access the viewing angle value from this instance, and the most important thing is to access the rotated sprites dictionary. We will do this again with the name input parameter. Now in the getAngle method, given the value of the view angle and the value of the number of angles, we need to get the correct angle index, and with it we will finally get the corresponding cached image. And let's look at the result of the cache. And as you can see, we got a tenfold increase in frame rate. This is an amazing result that will provide us with further development of the game. And by the way, for a greater increase in the performance of our engine, you can do one more trick. In the run pre-render method, we can choose not to use a transparent surface for the sprite, but instead fill that surface with a color we don't plan to use for the game, and then make that color transparent. And as a result, this approach adds another 100 frames per second to the performance, so we can say that the core of our game engine is completely ready, and now we can continue to develop the game without fear for performance. But at the same time, we got a disadvantage associated with an increase in game loading time and a higher consumption of RAM, but this caching system can be improved, and as an option, it is not necessary to pre-render the same objects every time. Instead you can save them to disk, and in subsequent launches, simply load from the disk, which will greatly reduce the loading time of the game. But we leave the caching system as it is, and let's now implement a player in our game. To do this, we will create a new file called player. Here we will import the settings in the math module. We will write the player class that inherits from the sprite class. It has access to our application instance and, accordingly, the rendering group. And for starters, as a player, there will be some surface on which we will draw a red circle and place it in the center of the screen. And then we can import the player class and instantiate it in the application class constructor. So our player is displayed as a red circle in the center of the screen, and let's make it so that the player will always be here, but all game objects will move relative to the player at some offset, which we get as a result of player control, and it will look like the player himself is moving. Then let's define attributes for offset and increments dx and dy. Through the move method we will change our offset according to the values of the calculated increments. And let's write the update method. Here we first call the player control method and then the move method. So, before writing the player's control method, let's define the value of the player's movement speed in the settings file. Well, then in the control method, first of all, we will reset the increments dx and dy, and in order for our game to be independent of the frame rate, we will recalculate the player's speed value, taking into account the value of the delta time between frames. Then we get the states of the keys, and implement the movement of the player to the was keys. For this we will assign the necessary increment according to the key, taking into account the Pygame coordinate system. And now it remains for us to take the player instance as attributes in the stacked sprite class, and use it to take into account the player's offset value when assigning the position of the object. And so we got the opportunity to move in our game, but with such control we did not take into account one moment, since we are allowed to move diagonally. Then with such a movement the player's movement speed is noticeably higher, unlike when moving when pressing one key. Look, let's say we press the D key and move to the right a distance equal to the value of the speed variable. In this case everything is fine. But if we still press the S key at the same time, then the length of the movement vector will already be much larger, and according to the Pythagorean theorem, such a movement to the root of 2 times will be greater than the speed value. To eliminate such a lack of movement is quite simple. Let's define a variable correction for diagonal movement. It will be equal to the inverse root of 2. And then it remains for us to check for pressing 2 keys at the same time. If there is one, then we multiply our increments by the value of this correction. And now the movement in our game is correct in any direction. And now I would like to move on to the most interesting effect of sprite stacking. This is the rotation of the entire game scene around the player. It is this effect that gives a sense of 3-dimensionality to our game world. Then let's define the value of the player's rotation speed in radians. In the player class let's define the attribute self-angle. For the speed of rotation we also need to take into account the value of delta time, and we will change the angle of the player by pressing the left and right arrow keys. Now in the stacked sprite class, based on the player's angle, we will get the angle at which we look at objects. And here we need a new attribute to determine the position of the object on the screen. And then we can write the transform method, in which we first shift the object according to the player's offset value. Then we will rotate this object relative to the player by the value of its angle, and at the end we make an offset to the center of the screen. And this method will be called in the update method, and let's set the position of the object according to the screen pos value. And so we got the ability to rotate all game objects around the player, no matter where the player is, and everything seems great, but look what happened to the player's control. Now our world is rotated by some angle. I press the W and S keys, and I get the player's movement in the coordinate system of the rotated world. This is very inconvenient and easy to get confused, so I want the control to remain according to the screen coordinate system as it was originally. That is, relative to the screen coordinate system, the game coordinate system is rotated by a certain angle, and accordingly our control is also rotated, and we will return control to the screen coordinate system only if we rotate the movement increments back by the value of the player's angle. And the easiest way to do this is to describe our increments dx and dy as components of a 2D vector, and then we can use the functionality of the Pygame module. That is, using the rotate rad method, we will rotate the increment for each key pressed by the opposite value of the player's angle, and we get the desired result. It remains to adjust our code to work with a common 2D increment vector, and let's run the program. And as a result, our player movement control remains in the screen coordinate system, and this is very convenient. That is, no matter how we rotate our game world, our movement directions do not change. And I would like to implement one more thing, which is to allow objects to have some initial rotation so that they do not look like they are all oriented in one direction. Then we can add an input parameter rot, for convenience, measured in degrees, which if we divide by the value of the viewing angle, we get the required offset of the angle index, which we will use in the getAngle method. Now let's give some initial rotation to our objects and look at the result. And as we can see, game objects are already differently oriented, and such a feature will certainly come in handy for us in further development. And at this stage, I propose to move on to creating a more diverse and interesting world for our game. And now let's create a scene file, where there will be a class called scene. Here we will have access to an application instance and call the scene load method. That is, the entire game world will be created using this method. That is, instead of directly creating game objects in the init method, we now need to import and create an instance of the scene class. So now I propose to create a map of our world, and for convenience, let's make it in the form of an array, and let's say it will be a 2D array of 9 by 9 elements. And if we define some symbols for the player and the names of the existing game objects, then we can easily put them on our map. By the way, we need to set the size of the map tile, and at the same time, let's change the background color and slightly reduce the scale of the objects. And to make it convenient to place game objects only within the size of our array map, the initial position of the object must be multiplied by the tile size value. So we can determine the size of our map and the position of its center. These are useful values in case of tracking its borders. And now we can iterate over our map array. Here we will calculate the coordinates of the tile center, and if this is a player, then we will set the offset value equal to the position of the tile center, taking into account the tile size, and for everything else, except for the 0 number, we will create an instance of the stacked sprite class. And if we run the program, we will make sure that everything works correctly, and all the objects that we have indicated on the map are in their places. Now let's see what happens if we place more objects on our map. And as a result, we see that we have a problem with the drawing order of objects. Our objects overlap each other, and since we don't have such a z-axis, we need to implement sorting along the y-axis for the correct drawing order of objects. But for this case, instead of a simple sprite group, we will use the layered updates group. Its peculiarity is that each sprite will have a private layer attribute, the value of which just determines the order in which the sprite is drawn. So our task now is to change this attribute using the changeLayer built-in method for our new group, and we will set it to the value of the y-coordinate for the position of the object on the screen. And also for the player, we need to set the value of the layer attribute, but only once, and it will be equal to the y-coordinate of the center of the screen. Let's check the result. And as you can see, by using the layered updates group, we have implemented the sorting of objects along the y-axis in a fairly simple way. So I want to continue with the fact that I added 2 more objects to our game. This is a tree and a car. To do this, I accordingly added the attributes of these objects in the settings file, defined the designations of these objects for the following symbols, and changed the map that you see on the screen. If we run the program, we will see a more lively and interesting world, but at the same time, we can now find another issue. If we let us stand next to the tree and start rotating the world, then we will see that the rotation occurs with a large deviation, and as if in our world, each type of object is located at its own height level. And this happens due to the fact that all objects have different sizes, but we have their centers on the same level. And the simplest solution is to define a new attribute in the description of objects that determines the offset along the y-axis, and such an offset for each object is selected individually. When we have determined this offset, then in the stacked sprite class we will create a new attribute y-offset in the form of a 2D vector, and in the y component we will assign the value of this offset. And then it remains for us to add this vector to the position of the object on the screen. And let's look at the result. The correct value of such an offset determines the absence of object deviation from the player when we rotate the world, and as you can see, all objects rotate correctly around the player, that is, they are at the same height level. Excellent. And now I would like to improve our visual component even more. Often in pixel art graphics the drawn objects have a clear outline, so let's also implement this effect for our game. Then we need to go back to the cache class and define the attribute value for the outline thickness. Now in the run pre-render method, I propose to create an outline variable, which we get from the object's attributes, but if it is not set, then for all objects this value will be true. So for such objects, we can get a mask from the formed surface and apply the outline method to it. This will be a set of coordinates for the points that form the outline, and then we can use the polygon drawing method on the surface of our object, and for this we specify these coordinates in the thickness value outline. Let's check, and as we can see every game object now has an outline. It looks quite nice and gives quite an aesthetic effect for using pixel art graphics. But let's see what happens if we add an object like grass. And then, with this approach, the grass outline is incorrectly formed. It looks like glitches due to the fact that the sprite itself contains several separate objects. And in fact, for such background objects, we simply define the outline attribute with a false value, and it seems to me that for such objects, the outline is not required at all. So at this stage, we have a rather nice graphics engine, but as you can see, all objects are oriented in one direction and are located strictly in the centers of the tiles. And here I propose to use some randomness. Let's create a function to randomly rotate an object initially, and the same function to get some random displacement. And now they can be used as initial parameters when creating new instances of objects. And thus, the arrangement of objects in the world, especially trees, became more natural, as if it were really a wild forest. And it's time to make a more interesting character instead of a red circle as a player, and I think simple 2D sprites will be great here along with sprite stacking objects. And to implement such a solution, so as not to duplicate a lot of code later, I suggest loading images of simple sprites in the cache class. We will also have a base entity class in which we get access to images and implement their animation method, and further classes, including the player, will be inherited from this class. So for the player and for all other 2D sprites we will use the following sprite sheet, the structure of which is exactly the same as for sprite stacking objects. Then we also need to create an attribute dictionary for each entity, and as you can see, it completely repeats the attribute dictionary for stacked sprites in its structure. And we also do the same in the cache class, create a separate dictionary for storing images and then call the method to get this cache. This method is similar to the method for stacked sprites, and the most convenient thing is that we can use the same getLayerArray method, which will allow us to get the entire list of images from the sprite sheet due to their same structure with stacked sprites. Okay, we have loaded the images, and now let's create an entity file in which we will create the above class called baseEntity to implement the animation. Here we inherit from the sprite class and define attributes for the application, name, and drawing group. After initializing the constructor of the parent class, we get access to the attributes of the entity in the cache, from which we now have access to images, and from the first image we get the value of rect. And for the animation, we define the index of the current frame. And by the way, we can check how this approach works, and for this, let's inherit from the base entity class in the player class, and according to the structure of the base entity class, we make changes here. And so our player finally has a pretty cute look, and it remains to implement his animation. It is worth noting here that the size of the player has become larger compared to the red circle, so do not forget to adjust the Y offset value for the sprite stacking objects. So the whole animation will be based on the firing of an animation trigger, for which we will assign a user event, which with the help of a timer object will appear every 100 milliseconds. And in the checkEvents method, we will track the occurrence of this event. In other words, our trigger will take a true value every 100 milliseconds. And now we can create the animate method. When our trigger fires, we increase the frame index by 1 and thereby change the image itself, and to loop the animation, we use the modulo operator for the number of images. And in the update method we make a call to this method. Then in the player class it remains to call the update method of the inherited class, and let's run the program. And as you can see, the animation of our player is working properly. Now the player has become lively and cheerful. And now let's look at an example of how to add another entity to our game world. So I have a sprite sheet for this cute kitty, and the attributes for this object are defined in the entity dictionary. Now we need an entity class, where we also inherit from the base entity class, and here we define attributes for the object's position, Y offset and position on the screen. The transform and change layer methods will be identical as for the stacked sprite class, but we will have a separate method for setting the rect to a position on the screen. And do not forget to call all these methods in the update method, including the inherited animation method. Then let's import this class in the scene file, define the designation for the kitten, and indicate its position on the map. And by the way, I use this method of setting a map for demonstration. For more complex maps and a large number of objects it will be most convenient to use a free map editor called Tiled, or similar. And now it remains to create an instance of entity in the position where we placed our kitty. And let's find our object on the map. And as you can see, we got the opportunity to place animated 2D objects in the game that can act as NPC and similar targets. And now I would like to draw attention to the fact that such an object as a tree often hides our player, and let's make the tree transparent in the case when the player is hiding behind it. Then let's create a class for transparent objects. Here we will inherit from the stacked sprite class and call the super function for the init, update and get image methods. And we will additionally store such objects in a separate list created in the application class, and when an instance of this class is created, it will automatically be added to that list. This list will help us find the objects closest to the player, that is, we need a method to get the distance to the player. And to activate transparency, we need to define a trigger for this, and let it be called alpha trigger. So we have determined that tree objects will have the property of becoming transparent, so in the scene loading method we will create instances of this class for them. Now all these instances are also in the list of transparent objects, which we can sort by the value of the distance to the player, and since the trees are quite close, let's say for the 2 nearest trees we activate our trigger, and we will call this method through the update method. And this method, in turn, will be called in the class of the main application. So if we display rects for objects for which alpha triggers are activated, we will see that we have 2 nearest tree objects on each frame, and now our task is to make them transparent when they hide the player. And for let's write a getAlphaImage method, which can be done in a fairly simple way, we check the value of the trigger, then check if the middle of the tree is below the player's head and check if the player rect is inside the tree rect, in which case we set the image to some value transparency. And let's check. So the trees really become transparent and we got a nice graphical effect, and this approach is quite suitable for our case, but it is not universal. If you want to use objects like bridges or arches, then it is better to look towards overlapping object masks with the player. And at this stage, we can say that our graphics engine is ready, and the purpose of this video was to consider exactly the details and nuances regarding the graphical implementation of the sprite stacking technique using the Pygame library, but I also implemented the collision system and shooting mechanics. The source code of this game concept is available at link in description. Well, as you can see, using the sprite stacking technique, you can achieve very original and aesthetic graphics, and then choose for yourself what genre of game it will be, adventure, role-playing or zombie survival.